So we were talking about the question of collisions and what happens when to the Boltzmann transport equation, and the point was what the Boltzmann transport equation was doing was essentially telling you that how the probability, how the probability distribution for velocity, the f of v r t, how it would get to equilibrium situation where that looked like del f del t plus v dot del f del r plus any external force dot del f del v equal to a right hand side. And what this right hand side did was essentially the kind of right hand side we had was one in which elastic collisions alone figured, but there was equilibrium for f equal to 0, no external forces. We found the equilibrium distribution, which makes del f to be the Maxwell-Boltzmann distribution minus mv square over 2kt. And if I were to disturb this equilibrium, then there would be a relaxation. So if you if I disturb the equilibrium, then there would be, number one, oscillations, which we almost showed, but then that is in the first order in perturbation theory. But second order, there would be relaxation, and you would be coming back to equilibrium. So that was the principle of the Boltzmann transport business, that you write this down and write out a transport equation. You have a right-hand side which features the collisions which make the system come into equilibrium. The equilibrium distribution exists. Then if I disturb the equilibrium, if a disturbance can get carried, which is in the form of waves, which is the sound wave, better be carried. Otherwise, we would not be listening to anything. And then it damps out, better so, I guess, also not much point in, for example, this class being audible across the street and disturbing the classes in the university, for example. So better get damped out. So and get the equilibrium back. So everything we did not demonstrate the relaxation. That's formidable, another bit of formidable calculation to do, but that was the principle. So all right, that really is the way to do it if you really want to study deviations from equilibrium, and how the equilibrium is approached by looking at exactly what the molecules are doing. Then this is certainly the way to go about things. Obviously, as must have been clear over the last couple of days classes, that this is a very ambitious program. So what you want to do is look at alternatives. How do I describe this process of achieving equilibrium without working too hard? So one way was the following, which the whole business is a little problematic. How the historical bit. 1905 came Einstein, with his explanation of Brownian motion. Brownian motion was this business of particles just moving around. I mean, this is dust particles in air, essentially. So dust particles in air sort maintaining sort of not essentially, let's say, defying. They have a there is a in the gravitational field they have a distribution, and that distribution, if this is z, then the distribution is minus mgz over kt. So that's the density distribution of the dust particles over here. But at a given z, they are sort of moving around. They are not static, and they are moving around, but it is equilibrium in the sense that the number of particles in this room or they are not the exchange energy and do whatever is needed. I mean, the collision process, exactly as over here, manages to keep them in equilibrium. So, but the question is that they are moving around, and in this situation where you have a set of particles which, as in the dust particles in this room, as I said, is a very good example. They are moving around, so there is displacement. There is no obvious external force over here, and so kind of what kind of dynamics are they following? You know what the velocity distribution of particles are, which is the now in the distribution of velocities, dynamics are these particles, do these particles have, if I were to write down Newton's law for each of these particles, what would I do, and what would ensure that there is underlying equilibrium distribution in it. So you want to, and what the 1905 contribution of Einstein was, that these particles move around in a manner where, if I look at the mean square displacement, x square average, then x square average, I mean, it is it has to be three-dimensional, so r square would be, but 1D is good enough for what we are saying, that x square average is proportional to t. So that was the Einstein contribution of to Brownian motion in 1905, that if I look at these particles, on an average, the kind of dynamics that they have, if I look at if I were to focus on a particular particle and look at its position as a function of time, what would happen is that on an average, it wouldn't be going anywhere. I mean, there would be a question, the dynamics would sort of, as a function of time, look very jagged, and it would probably be a graph which looks like this. So that is what the dynamics is going to look like, x as a function of t for an individual particle that you are looking at. So on an average x is 0. So this is not a dynamics, I mean, where you can actually talk about dynamics is not where you can talk about x as a function of t. That would be that is not on. I don't want to look at, I won't be able to calculate x as a function of t, but I can certainly see, for example, that average x is going to be equal to 0. But and similarly, if I want to look at average of the velocity, then that average velocity is also equal to 0. But if I want to look at x squared is certainly not 0, because you have to square, I mean, they would all become of the same sign. Then you would have to add them up. All displacements, I mean, if it's x squared would be on the, and x squared would have a, and similarly, v squared would, and that's the temperature, of course, the x squared, v squared, and x squared was what Einstein obtained, would be proportional to t, opening up a completely new kind of dynamics where you don't have an average displacement, but you do have a displacement which you characterize in terms of x square average, and that turns out to be proportional to t, which is why, I mean, if I were to make get a length out of this, out of x squared, if I were to get a displacement, I would have to take a square root, and that displacement would be proportional to t to the power half. And therefore, if I were to take a derivative of this displacement, which is like a velocity, then that would be proportional to 1 over t to the power half. And if I tried to take the limit of t going to 0, it would blow up. So that is why, I mean, these are funny, I mean, these are non-convex. You don't describe this a kind of motion in normal terms. You have to look at it in a somewhat different fashion. And all right, so Einstein worked out the average x squared with a probabilistic description, and which was not exactly very easy, and therefore a couple of years down in 1907 there was a different 1907 Langevin, who was a very close friend of Einstein, tried to make it somewhat easier. So what we will be talking about is how Langevin looked at the dynamics of these particles, which are sort of randomly moving around in the atmosphere, and how does one get a hold on them. That is, hold meaning that I start out with Newton's law and then sort of try to, obviously, as I said, this has nothing to do with Newton's law. Newton's law gives me x of t, and dx dt is a well-defined thing. That's a velocity. And over here, if I want to get x, it would have to be calculate x square average, take a square root. The x square average goes, and therefore defining a velocity is no longer possible. So, all right, Langevin had to figure out how to use Newton's law over here, and what would the mechanism of getting answers be. And the point where what he focused on was that, look, the primary thing about this motion that is going on, essentially a random motion where particles are coming and hitting each other and sort of not going too far, and but there is it's a sort of random motion on which you don't have any control. So let's focus on a single particle, a given particle which is over here, and it's getting hit continuously by all particles from above, below, and the sides. So there are all kinds of collision processes going along. And let's say this focused particle, the particle on which I'm actually concentrating, that is why I have drawn it a little bigger and have shaded it. So this particle, let's say, has a velocity v. So this particle has a velocity v, and it's being hit by all particles from the front, sides, and top and bottom, everything. Now, there is a difference between, so number one, what am I after? I'm going to write down dv dt. So I want dv dt is the acceleration, which is equal to the force. So dv dt is the force. So that is Newton's law. So I have to write down Newton's law for this particle over here. So that's Langevin's starting point, that I want to write down Newton's law. I want to write. Now the hits are completely random. So if these hits are completely random, then there has to be a component of this force which is a random function. So and what do I mean by a random function? What I mean by a random function is function. Let's say the function over here is a function of time, and the random function f of t means that I don't exactly know what the precise f of t is, but I only do not know precisely, but can only say what is the probability, of its being given f of t. So it's a question of being all that I can say that there is. I mean, I can write down. I can write formally f of t, but I don't know what is the what exactly it is. But I know that it is what I will call a random force. A random force, meaning that I only can talk about the probability of the force being a particular function f of t. It can be a whole variety of functions, and it is I'm writing a particular, giving it a particular form, f of t, I mean functional represent f of t, with the understanding that all that I know about f of t is that it has a probability distribution instead of being a definite function. So it's that is what I mean by a random function. So all right, at there is going to be that part, but there is going to be another part of it, because if I look at this in the let's say the rest frame of the particle, the particles which are going to hit it from the front, they are going to hit it harder. So if I look, it's you can, I mean, there is asymmetry on the hits that it's being that this particular chosen particle is receiving. If this chosen particle at this instant has a velocity v, then you can differentiate between the hits from the front and hits from the back. The hits from the front are more effective. The change in momentum of the particle which comes and hits it, because in the rest frame, if this particle has a velocity v and this the collider is now going to have a higher velocity. If the collider's velocity is u normally, then in the rest frame of this, you will be seeing velocity u plus v, while the one which is coming from this side will have a velocity u minus v. So the momentum transfer, elastic collision, collides, goes away with minus u plus v, so imparts a bigger hit to it. So there is a change in momentum which is in the backward direction. This chap comes and pushes it in the forward direction, but it can only give an amount minus this is amount of momentum per unit time. You can only the amount of momentum. You can only this one can only give a momentum which is u minus v times n, and that is not sufficient, and therefore this particle will feel a resistive force which is proportional to its velocity. So that is the key point. One of the two big points in this Langevin equation. When you write down the dV dt, then dV dt has a resistive part which is minus gamma v. That's clean resistive force, which is like any other, I mean, friction term that we write down in Newton's law. So that has to do with this net effect of the collisions, and the other is random force f of t. So that over here, dV dt equal to minus gamma v plus f of t, this resistive resultant resistive force, and this random force on the motion. That's the decomposition, the physical decomposition of the right-hand side of Newton's, the force side of Newton's law. The same effect, the collisions. Mind you, the very important point is that it is the origin of both these terms, the minus gamma v and the random force f, is the same. They all come from these random hits. Because this particle at any instant has a velocity and is trying to move forward in that direction, the random hits has to slow it down. So there is this definitive not definitive, there is this non-random part, that is minus gamma v over here, and then there is this random force, which is the rest of it, which on an average is equal to 0. So on an average, f of t is equal to 0. What on an average? What is it on an average? What do I mean by on an average? Well, there are two ways, once again, of taking this average as you would know from the earlier StatMech courses, that I could look at it as a function of time and consider this force. At this instant, this is the force. At this instant, that's the force, and so on and so forth, and add it up and take a, that is 1 over t integral 0 to t ft dt. That average value would be equal to 0. Sometimes it's positive, sometimes negative, so on, and sometimes in this direction, that direction of it goes. That would be 0. Or you can think of this as look, instead of focusing on this particular molecule, you look at focus, put your focus on that, and for this, at this instant, the force is some f of t. For the, let's say for this one, it is a force f1. For another particle which you focus on and similar hits, the force is some f2, and you can average over the different particles at a given instant, and you would get the same, you could construct average over the different particles that constitute the system, and take an average of the force at any instant, and that average would still be 0. So that's either you do a time average, or you do an average over the different particles over here, ensemble average, and the ensemble average and the time average, they both would give you 0, and that's what ergodicity is all about. So, all right.
Sir?
Yes, go ahead.
Sir, over here we are working in equilibrium, na? Means since we have ergodic hypothesis applied.
Equilibrium
Means what we are saying, what I'm saying is that the time average of the system is equal to the space average that we are taking. So,
that is a property just of the dynamics, right? Which allows me to write a probability. I mean, at some point it would allow me to write a probabilistic description without making an error. But the dynamic, it is the characteristic of a dynamics that characteristic of a class of dynamics which says that if I look at a chaotic system, then I could, which all these things are, whether I construct an average by time averaging or construct an ensemble by, so it sets up the foundation for statistical mechanics, but equilibrium statistical mechanics. But the foundation has nothing to do with the fact that in the dynamics you have, if I'm considering it's not the equilibrium system and the probability distribution that I'm looking at. I'm in the business now of looking at exactly what takes you to equilibrium, and that has to do with the dynamics that and what kind of a dynamics do I have? I have a dynamics which shows ergodicity for it, whether if I there is a random process going on over here, and the thing is that its time average is the same as an ensemble average. So that is a property of the dynamics and not a property of the let's say not much to do with the equilibrium stat-mech that we talk about, except that all right, I mean, this tells you that you can use this ergodic hypothesis to justify the existence of a equilibrium distribution, but even that is a little bit tricky, because at the end of the day, equilibrium stat-mech would have to say that a far stronger statement that all the microstates associated with the system are equally probable. So without that, one wouldn't be going anywhere, and that is certainly not being used. We are simply saying that the dynamics is going to be ergodic in the sense that I can construct averages in two different ways, and the ergodicity is a property of the chaotic dynamics. So it's a chaotic dynamics which is what one is talking about.
Got it, sir.
Yeah, go ahead. What is the cause? Cause are just the collisions. I mean, I have 10 to the power 23 particles or 10 to the power 20 particles in a small region. So they are, I mean, if I have a temperature, then they are moving. And if they move in a spot, they collide. That's the cause of the dynamics. The minus gamma we term as if at any instant I look at a molecule, it has a velocity in a particular direction. The other particles are going to come and hit it randomly in the next 10 to the power minus 20 seconds. And those which are hitting it from the front are more effective than those which are hitting it from behind. Therefore, on an average, there will have to be a resistive force. So there is the random force that we are talking about. If this particle is going to sit there with no velocity, and if I put a block over here and get particles to come and hit it, then the answer is there is only one force, which is the random force. But if this is a part of the system which is being considered and it too has its motion, then at any instant, if its velocity is v, there is, I mean, if it, meaning that I can look at things from its rest frame, and from its rest frame there will be a force which, after I have summed over all the particles, that force will be a macroscopic resistive force in this direction. And which means that if I take just a second, which means that if I take an average over the different particles, then this average is going to be 0, but this is going to be not, this part is going to be a decay, which would bring this particle to rest. So that's the difference between any time I have a velocity and I'm being randomly bombarded from front and behind, then the random bombardment has to be taken into account by this kind of a force, a random force. But there is something more than random. There is a force. If I'm trying to move, then it will oppose me as a net effect, and I will have to take that effect out in over here as a separate effect, so that I can confidently say that average f of t is equal to 0. Get it? Yeah? So all right, so that's essentially one part of this microscopic business, which has a average 0, is being taken out, which is an effective resistive force, which is, I mean, which is what sometimes you can actually calculate it. If I put a sphere in a liquid, the force is 6 pi eta RV. So a slowly moving sphere in a liquid, there is this resistive force, which is 6 pi eta RV, and this is, if I were to consider a liquid in which a particle was moving around, I would put down that force as a 6 pi eta. That, I mean, for a given a small sphere moving inside a liquid, the liquid comes and hits it from all directions. But if it has an initial velocity v, this sphere actually moves along. The difference in setting is that this is a small ball which I have put externally, and is a resistive force, which is, I mean, the viscosity and the coefficient. The gamma is like the viscosity of the fluid, that's the resistive force. So in a slightly bigger situation that is talking about a sphere falling through a liquid, the way it reaches its terminal velocity is through the and that's the force that we have over there. Yeah, this is the wrong board anyway. Good. So that's the picture. All right. So DVD. So that is called the Langevin equation. So question is, I want to write down a solution. Average, as I said, average f of t is equal to 0, and let's first write it in terms of the idea for, let's say we want to, if I'm going to do dynamics, that is, I want to track how the motion of a single particle, the motion in coordinate space, then I would be writing this as d2r dt square plus gamma dr dt is equal to f of t. Not that it helps me very much. Sorry, the force. All right. Vectors are nuisance in some ways. So let's make it take a this is essentially the the 1907 Langevin verbatim. So I take a dot product and with R, so that I don't have to deal with vectors and can talk about also two motivations over here. One motivation is that we're dealing with scalars, but there is a deeper thing. I would not, I mean, what the 1905 Einstein paper had shown that good. So, with this, let's look at ddt of R dotted with yeah. So this is equal to, so there are going to be two terms over here, which is R dot R double dot plus I'm going to get R dot square. So R dot right. So R dot R double dot, which is what I have over here. So that can be written as R dotted with R double dot and R dot square over here. So this is my would that help? Well, all right, that's this is R dot double R. All right, this is want to take that and make it, you certainly want this out of it there. 1 second, this is only takes me halfway there because there is R dot, there is R dot ddt of R square over there. So there is a ddt of R square. So I want actually something which would give me there, if I have ddt, I want it in the form of R, just a sec. It's ddt of R dot V over here. R dot V is not convenient so much. So you want it, I want R dot V is, I'm in the business of R dot dvdt. So it is R dot, there is a R dot dvdt here. There is a R dot, what am I looking at? That's R dot dvdt, which is what that term is. And it is a ddt of R dot. All right. So this is ddt of R dot, fine. And then this is ddt of R, so that is half, all right. So R dot ddt of R. So it is half, and that's ddt of half ddt of R square, and that is equal to R dot R double dot plus R dot square. So I can now write R dot R double dot, that has now become half d2 dt square of R square minus, so this is R dot R double dot, and minus R dot square plus gamma ddt. So if I put a 2, gamma by 2, R square average is equal to R dot F. Very good. So all right, half, so that makes it, now I can get rid of this here. So my dynamics has become d2 dt square of R square plus gamma by 2, there is a half here, there is a half here, F. All right. So now so now what? All right, this is at this point I have to get rid of this term over here. So without that, I'd make no progress at all, and therefore I focus on not a complete solution of R square, because that is going to be a random function. All that I want to be satisfied by knowing what R square average is going to look like. So R square, I ask a much more restricted question. Up to this point, I am exact. So up to this point, I'm doing things exactly. At this point, it is R square average which I want to look at, because I have no control on this right-hand side. And yeah, so I make use of the fact that average F is equal to 0, and then look at. And as soon as I do that, it is half, or let's get rid of the half, d2 dt square of average R square plus gamma ddt of average R square is equal to average of V square. Now is when the Maxwell-Boltzmann relation comes into use. So V square average was given by Maxwell-Boltzmann distribution as 3kT over M. So that is what you get out of what you learned over there. And therefore, this equation is d2 dt square average R square plus gamma ddt of average R square is equal to 3kT over M.
Sir, এটা
Yes?
half ছিল না আগে?
Huh?
এটা half ছিল না?
Half ছিল সেটা, ওখানে 2, yeah, thank you, half ছিল। Thank you. Yeah. So it is ddt of this. So now, all right, now something which I can solve. Now it is ddt first order equation in terms of ddt. So if I so far as ddt of r square, if I call this x, then this is dx dt plus gamma times x is equal to 6 kt over m, and this x over here then is solvable as equal to integral e to the power the integrating factor is e to the power gamma t. So you go 0 to t. So I'm going x of t equals 0 to t e to the power gamma t, with which I have multiplied both sides, and it is 6 kt over m e to the power t dt prime. And then there is, once I have done the integral, on this side it is ddt of x e to the power gamma t, and therefore I have to have e to the power gamma t with this plus a constant of integration and e to the power minus gamma t, right? So that's the answer. So this is equal to e to the power minus gamma t, and then I have to do this integral over here, which is thankfully not much to do, and I have a gamma which comes from here, and I have e to the power gamma t minus 1. Let's choose the take it to be 0. Always, all right, or let me not keep it for the moment. So this is equal to, so average x of t is equal to 6 kt over gamma m minus 6 kt over gamma m plus c and e to the power minus gamma t. So there we are, and that's the solution for x, and you can now go ahead and in. So what have I got? So I have got this, and now it is average r square is equal to 6 kt over m times t, and then you are going to pick up it's 1 over gamma. So e to the power minus gamma t has to be integrated. So it gives you 1 over gamma minus in the denominator. So there is 1 over gamma, and there is 6 kt over gamma m minus c1. If I now call this constant as c1, so it is c1 e to the power minus gamma 1 t plus c2. So two integration constants, because it was a second order differential equation, and that's that. Well, t large. So when a long time has gone by, this term is going to go to 0. Average R squared thinks you choose your constant C2 to be equal to 0, or I mean, you don't even, whatever it was, you don't care. R square average, when T becomes very big, R square average is equal to 6kT over M times. So there is Einstein 1905, obtained in a very different manner, that you have this R square average. You write down dynamics for the particular chosen particle in this swarm of particles undergoing random motion. You choose a particular particle and you see what's happening to it, and you want to see how far it's not going to, there is no mean flow, so it is not going to go away very far, but it is going to undergo a random motion for which the average is 0, but the mean square average, the square of it has the value which increases linearly with time, which is the Brownian motion answer. So this is this is what Langevin equation does for you. This is the standard operational technique of working with Langevin equation. You have this force and if you are looking at a system which looks like dV dt plus gamma V is equal to some random force. And this we have not talked about the random force at all, but we have obtained an answer which is independent of what kind of a random force it is, that if all that I know is that under that dynamics, the velocity has to be a random function, and therefore, I mean, so the particle displacement has to be something which is a random function as well. And if I look at so on an average, it doesn't go anywhere, but if I look at the R square average, then there is silence. So that's the that's Einstein 1905 made easy. So that is what but apart from that, what this opens up is a completely different kind of maths. You talked about talking about a differential equation in which there is a random part. That is, so what it started out was this whole business of stochastic calculus. So that's branching out, that there is this differential equation with a random term in it, and you need to know the solution of it in order to get a physical answer. Yeah, go ahead.
So you said that initially the system is not in equilibrium, right?
What
initially? No, not initially. My system is not in equilibrium. The whole Brownian system.
The system is never in equilibrium.
Okay. So
we have,
how we are using that V square average is equal to 3kT by M. This is a Boltzmann, Maxwell Boltzmann, and Maxwell Boltzmann was for the equilibrium case.
Yeah.
So how we are using it, sir?
Well, all right. The point is that not in, there is dynamics going on, obviously, but the point is also, it is also true that you are not too far from equilibrium. If you were very far from equilibrium, then, I mean, this is again the scenario. That's a very valid question, actually. It is still a scenario which is just like the Boltzmann transport that we had done. There was an equilibrium distribution that we calculated, and then we looked at perturbations around it and how the perturbations behaved as time. So that's exactly what we did, and that's what we are doing once again over here tacitly. And that as soon as I write down that this V square average is something that I know, that V square average is given by, it is the radius which is, so where the particle will be, that is what I don't know for sure, because, but I'm not so far from equilibrium that all this is happening at a temperature T. There is a temperature. The underlying statement is that there is a temperature defined in the system, so that I do have there is some concept of equilibrium there, because there is a temperature which is an equilibrium concept, and that comes from the fact that it is the average value of V square, which is the temperature of the system. That is well defined, and I use equilibrium distribution function to get at it. Yes, right. I mean, there is, as in almost all calculations that one does, what do you call it? Perturbative aspect of it, that what is being considered, which average values are deterministic. Well, it is the V square average which is deterministic. That is fixed through the Maxwell-Boltzmann distribution, but it is the R square average which still has a dynamics. V square average may be fixed, but given V square average as fixed, what does R square do for R do for you? Well, R square still drifts. Even though the V square is determined by the temperature and is 3 kT by m on an average, the position vector still has a diffusive motion, and that diffusive motion has, that is the diffusion coefficient over here is still defined, well defined, and defined in terms of a temperature by this. Yeah, so that has to be there. I mean, otherwise, I mean, we would not be able to, there is equilibrium in some sense, in the sense that I can define a temperature of this room, and therefore I have all the moments of the velocity with me. But given that you know the moments of the velocity, you still, how do I get at I can obviously see that there is a random motion of the molecules. So how do you get at the random motion of the molecules, the average value of that? And that displacement is not something which is a constant. It turns out that that display is determined by the temperature. The diffusion coefficient is determined, its coefficient is determined by the temperature, and it's going to go, grows, the mean square displacement grows linearly in time. So yes, right. I mean, you mix things.
Got it.
As yeah, convenient. But over here, I mean, that is the there is still a temperature in the system. So in a fixed temperature bath, the particles are moving around. The fixed temperature allows me to talk about a V square average, which is time independent. But given a time independent V square average, I looked at the R square average. Sure. Yeah. All right. So this is the.
Sir, that means for far from equilibrium systems, we cannot actually apply these type of ideas, I mean Landgraf equations.
I mean, see, if you are really far from equilibrium, the temperature would not really be well defined.
Uh-huh.
There would be local variation of temperature.
Uh-huh.
So over here, I have a well-defined temperature. See the point, I have a well-defined temperature, but I still have molecules moving around. So this motion is the motion of molecules which are undergoing, I mean, drifts as, I mean, because the molecules are, I mean, moving around. There is no doubt about it. So the molecules are moving around. They have a velocity distribution, but the random motion of the molecules, if you want to look at what is happening to its position, it's not deviating from in the mean from its position either. The average R is still 0, but it has a dynamics. It's not that it is at rest, and therefore there it has some movement. So its R square average is equal. Its mean velocity is 0. Its mean position is always the same. So the mean velocity, obviously, of these molecules, they don't have a mean velocity because I don't have a flow over there. But as the velocity has a distribution, the R also, the radius has a distribution. The average position is not changing, but the average R square is changing. So the velocity, with the velocity, life was easier. I mean, these moving along, particles moving along randomly, the average V is 0. I mean, Maxwell-Boltzmann distribution tells you that the average V is 0. It's not that the average V is a finite quantity. So Vx average, Vy average, Vz average, they're all 0. But there is a V square average, and that V square average defines the temperature. So these particles are getting hit and by other particles, and they are moving away from there, and I have to calculate what is the average displacement of the particles. None of them are running away. The average of R is 0. But there is a mean squared displacement. I'm calculating the mean squared displacement. In the process, I need the mean square value of V square, which is defined by the temperature, which obviously is time independent. And therefore, when I calculate V square average, I'm using V square average. I'm not saying that V for the particle is a constant. The particle has dV/dt and the V is changing all the time. But when it comes to the V square average for the particle, that V square average for that defines the temperature, and therefore it's this.
Yes, sir. Got it. Got it.
This is all right. The next thing around over here is sorry, there's something which I had to show. Sorry. Right, just a sec. And I need to point out a small thing over here which is interesting. R square average is 6kt over m times t, plus there was this constant over here, and that what I erased was a second constant, which is C2, and at t equal to 0, I can take, so I want to fix a constant C1 and C2. So at if I look at this at t equal to 0, R square average, let's say, has some given value, which would be obtained from this. So so ddt, I have a question of fixing the constants, let's say, by some hook or by crook, as t goes to infinity. I can't really use that. That goes to 0. Whether there is a C2 or not, I couldn't care less. But if at t equal to 0 is a different matter, t equal to 0, R square average is given by this, can't really take it as, so R square average need yeah, so probably the best thing to do is choose things. So t equal to 0. So t equal to 0, average R square is equal to 6. T equal to 0, average R square is 1 over gamma. So this is at the wherever I want to set the origin of time, 6 kt minus C1 plus the C2 over here. So 6 kt over, so that's average of R square at time t equal to 0. Suppose I just go ahead and I have to fix the integration constants. If I take set C1 equal to C2, then the answer becomes particularly simple. So let's just go with that. It won't have any bearing on the final issue which I want to address. 6 kt over m times t plus, and C1 plus C2, if I take it to be that, then it is 1 over gamma, and so this is equal to some C, let's say, 6 kt over gamma m minus C and e to the power minus gamma t plus C. All right, very good. Now the thing is, I mean, why this whole question of wanting to look at it? I want to look at small times. Small time, that is gamma t much, much smaller than 1. Gamma t much greater than 1, this goes off, and the answer is this plus this. At large t does not matter whether there is that or not, and the answer is the diffusion, pure diffusion, R square. So that's large t. I want to look at very small t. So at very small t, R square average is 6 kT over m times t plus 1 over it is so it's an what's this for? There is a gamma here, correct? This is r square over mt, and I have a just want to call this, don't do it this way. Call this, fix it so that it is, let me just keep it C1 plus C2, no, whatever. Let's put it at C1 as C2 for the moment, and then we'll see what the choice should be. The vital thing is elsewhere. So, all right, it is r square average. So is 6 kT over m t plus 6 kT over m gamma m plus some C1, and now because it's I can expand, it is 1 minus gamma t plus something plus C2, and then it is look at what I want to focus on is there is this 6 kT over m plus C1 that's the one part of it, and then there is the 6 kT over gamma m plus into minus gamma t. There is this C1 with this gamma over here with a C minus gamma C1, and this might. But the issue is, that is what I mean would fix this 6 kT over m times t, that is going to be exactly cancelled by this term over here, the linear term in the t, which involves the 6 kT over m, is going to go out, and I should have been able to, that is the vital thing to show, that if it is at if it is at small time, then the point is that the linear term which I have, the second order, I should have been, been careful about this, that I should be setting up the r square average need to know a little more than just r square average in setting up the C1 and C2. I should have looked at r square average and dr dt to get the C1 and C2. But that's that you can do for yourself. The important issue is the part over here, not the C1 and the C2. C1 and the C2 are only trivialities. So it is 1 minus gamma t plus gamma squared t squared over 2 and so on. And it is this part, the one just gives a constant in things, nothing important, but it is the minus gamma t with this will cancel the 6 kT over here, m over here, and that's what you will focus on. What you will be left with is a term, that is where, the point is, as I said, this C1 would have to, if one looked at the initial conditions, fixed it properly, the C1 would not be there. So please, get that done. The issue is that this term and this term would cancel at very short times, and the motion is r square is like t square, which is the standard answer. So r square over t square is the regular motion at very short times. So at very short times, it is, if I go to gammas which are so small that at gamma t is much less than 1, then the stochasticity that we are talking about and which is giving me this strange behavior where r square average is like t, that goes away, and r square at very short times is proportional to t square, and as time becomes bigger, this short in is actually the gamma t much less than 1 is the gamma is reasonably big, so short over here means really short. I mean, it's it's less than a millisecond. Typical gammas mean that this condition is t less than a millisecond, and there you see a growth which is like t square, and then you have this r square proportional to t. So there is a crossover. What I'm after is that there is a crossover over here, and come 2000 something, this crossover was actually seen in an experiment. I mean, people wanted to have, experimentalists wanted to have a look at it, go to regimes which are small time enough to see a crossover, and one could really see it. So that's quite, that was quite interesting. So that's a point which is worth. So all right, there is a what I'm after is that there is a short time and a long. The answer that r square average goes like t is a long time answer in the sense that that is valid if gamma t is much greater than 1. For gamma t much less than 1, you have there is a regime where this is like t squared. All right, so that's worth knowing. So as I said, it's an experimental fact today. So that taken care of. All right. The next business over here is that, look, I mean, how did it all the dynamics is usually just is Newton's law. So how did I get here from Newton's law? One should have the passage clear in one's thinking that there was, I mean, Newton's law should have described the dynamics but I now have a different kind of dynamics to talk about. So where exactly did this breakdown happen? When did Newton's law actually become that it is dv dt plus is equal to minus gamma v plus noise? So this structure, starting from a microscopic picture, can you get at that? That's something which people looked at quite, and I won't get into that in detail simply because it's a toy model which will take a lot of time. But if you are interested, you can actually work it out. What the model that one took is that it is characterized by a Hamiltonian which looks like p square. So unit mass, let's say, p square over 2, and you have you focus on this particle of unit mass, which has this kinetic energy, which is p square over 2, and then there is a set of particles with momentum, let's say pi, with kinetic energy, which is pi square over 2m, and the potential, so there is a sum over I over here, and the potential energy is half, and then it is xi minus xi minus there's some omega, yeah, sorry, 1 minute before I write this one, a set of oscillators, so half and m omega square xi square, so p square over 2, that's a particle of unit mass. Here is the heat bath, which is summation, so I equal to 1 to n, I equal to 1 to n, that's there. And then there is this interaction term, which is, say, a half omega square, and then it is x, which is this coordinate, minus a suitably chosen coefficient gamma over omega square xi squared. So that's the Hamilton quadratic all through, but here is the Bath variable. Here, rather, here is the characteristic of the frequency of the x variable, and they are coupled. The I, this I equal to 1 to n forms a bath, which will be characterized by a temperature T, and x is the particle for which you are interested in, you are trying to follow, that is the particle whose dynamics you are going to follow, so to see whether you get an equation of this kind or not. So this is Hamiltonian, purely Hamiltonian description, and then you use the Hamiltonian equations of motion, xi dot equal to del h del pi, pi dot equal to minus del h del xi, and x equal to del h del p, and p equal to minus del h del x. So you write this down, and what you would find that this is exactly solvable as expected quadratic system, and you can arrive at, from here to here, there is a passage when the n, which is n very large, and set this not only very large, and sets up a bath characterized, sets up a bath which is characterized by temperature T and Maxwell Boltzmann distribution. So that's a very interesting, it's an interesting exercise. You can, the original paper is due to Zwanzig sometime in the 70s. And subsequently used extensively for various types of approaches to systems which are sort of trying to come to study the approach to equilibrium. And the point is that if you look at this system, you can, by making appropriate approximations about the different parameters of the system, you can actually arrive at a structure which looks exactly like this. So then you know, but in the process, as I said, you would have to give at the end of the day, the I variables would have to be taken to be distributed with a particular distribution, which you obviously take to be Maxwell-Boltzmann distribution, and with that under control, you arrive at an equation which looks absolutely the same as what we have over here, giving the f is in terms of the parameters of these Bath variables. It's a sum over I with all right. What about the Bath variables? I mean, it can't be in terms of the xi and so on. They are in terms of the initial values of the xi and xi dot. It is the initial values of xi and xi dot which are taken to be distributed with a Maxwell distribution, and they are the ones, the initial values xi 0, xi dot 0, 0, they determine the damping coefficient over here and the random noise over here. And you have a very nice demonstration of one of the very few demonstrations actually where you actually start from a Hamiltonian, a completely prescribed Newtonian system, and you come up with, at the end of the day, with a Langevin equation with the some things averaged over, the I variables, I things, the Bath averaged over, and as a. So that's something which I would, I mean, encourage you to have a look at. It's a very clear cut. It takes a while. I mean, if I were to do it, it would take me more an hour. So that's not really practical, because at the end of the day, you at the end of the day, you know that all that you know is that, look, I mean, what we are saying, that there is equilibrium set up by a Bath, and what is happening is that at a fixed temperature where you are in it, but there is a question of the dynamics of the particles that are constituting the system. If you still want to look at the dynamics of the particle, then the dynamics has to be with an equation of this kind. So we started out by saying that the equation would have to be of this kind. This particular thing, I mean, gives you, it's always at the back of your mind that this is not a natural equation for a starting point of things. Natural starting point is particles and their interaction, and so it was really a path-breaking sort of thing to at least set up a system where, starting from here, you end up with something which is exactly like that. But that is where the action is really, and so all right. Another example of this, it's a question of what is called, I mean, what we have been looking at is a situation where the equation of motion looks like d2 dt square of x. What we wrote down a few minutes ago, d2 dt square of r plus ddt of r square, and that was equal to that was this kt over m sort of thing. Yeah, that's what we had. And this was the r square average, really. I mean, and then when you take an average, you get this kt over m. What is missing over here is a term. I mean, that is, it's not, we consider a system for which that is the way things are. It is dv dt plus gamma v equal to f. And there was no regular force to talk about. So if there is, suppose there is particles, these were free particles which were moving around, and if they were not free particles but were, let's say, in a oscillator potential, then there would have to be an additional term which looks like this. So an additional term which looks like this, and then you would have to look for the r square average and the solution. Once again, solvable, because that's there is no difficulty in solving this differential equation, and you get r square average as a function of time, and certainly at the end of the day there would be the regime where it would be r square average going like t and so on and so forth. But the interesting point was about this, that what kind of is that, do I have the Brownian motion was this one over here. What is, if I do, I mean, almost always one thinks of, I mean, if it's mechanics that have an oscillator potential, and you'll get something more richer. So do I have something over here which is interesting? Because as you can see that there is an equilibrium state, r square equilibrium, which is equal to kt over m omega square. So there is, instead of probing velocities, you want to probe the distance variable, which is somewhat the coordinate variable, somewhat easier thing to probe in a sense, then that would tell you that if there is a dynamics which is of this kind, then you would be able to probe the r variable, and you get r square. So question is, do I have a system of this kind? So can I actually set up a system which is a nice physical system which would fall into this category? So when people looked for this, and there are a couple of examples, of which one of the best is to go to the electric, electrical systems, and talk about charging capacitors. So charging capacitors in LCR circuit. So you want to do charging of capacitors in a LCR circuit, and now look at the various terms. The various terms are L di dt. So various terms which are producing the voltage. So our potential difference, that is. So you are writing down the equation of motion. There would be L di dt, which comes from the inductance. So that is the voltage fall across the inductance. The voltage fall across the resistance is I times R. And then if I have a capacitor in the system, so then there is Q over C, and that is equal to the external, I mean, the potential source. So L di dt plus IR plus Q over C, and that's equal to that. Not looking, and now you realize that Q is that I, the current, is dq dt. So I, the current, is dq dt. So this is actually L dq dt square plus R dq dt plus Q over C is the external V of t, whatever you may have. So this is something which you are all must be familiar with, the standard LCR circuit. And the point with this is now exactly similar to this, except that the V that you use, you are accustomed to writing the V as e to the power I omega t. What this is saying that now I want a V which is a random function. So you want a V which is a random function, and that does happen because there are these, if you have a resistance in your circuit, so these resistance has a strong electron motion. So the electron motion in the resistor leads to there is a fair amount, I mean there is dissipation this in the resistor, there is a dissipation, the maintenance of, again the current does not decay because there is a corresponding fluctuation that keeps the current going. So in the steady state, in spite of the dissipation, there is a fluctuation which keeps you going, and that is where you can actually, so what this V comes up, what this V is for our purpose, what this V is a fluctuation which is generated quite normally in the current carrying resistor. There is a fluctuation in the current coming from the fact that there are these the dissipation which goes out as heat has to be sort of naturally maintained. So that is called, that maintenance is through the fluctuation. So one can talk about fluctuation over here, and one would have, as soon as you have, this is exactly identical to what we were talking about, and therefore you would have some kind of fluctuate. This is the fluctuating part of the charge, and therefore this is a fluctuating part of the voltage. This, what you are seeing over here, is the fluctuating part of the charge, and corresponding there would be a fluctuating part of the current I, and this is what this fluctuating part, there would be a I square average or a Q square average, as the case may be, is what is known as the Johnson noise, the short noise, or Johnson noise, which was predicted in the 30s, I think, and over the later years. quite. So the application actually of what we were talking about comes in a wide variety of fields, and this is one of those. I mean, so this is Langevin as seen over here with a potential energy term thrown into the bargain, and it is the electrical circuits which are a nice testing ground. It's also a question that it's a small point, but it's worthwhile that these fluctuations are actually going to put a limit on the accuracy of how accurately can you measure the current in a circuit. So if you are doing these electrical experiments, question of the accuracy having a limit, it is determined that limit is determined by the fluctuations in the current, and it's certainly there is a temperature independent part of it, and it sets a limit on standard things like, these measuring galvanometer deflections and so on and so forth. There is a limit to the accuracy with which you can get a galvanometer, a temperature generated limit to the accuracy in those galvanometer experiments. There's obviously a very small effect, but effect all right. And if you are going to do a high precision measurement, it's a factor that you do worry about. So that's really Langevin equation. Also, let me end with one we are talking about a noise over there, this the random force F. The random force F, so what's meant? It's a function of time. It's what we are saying is that F of t, forget the vector, F of t, this is the force that we have the random force, is essentially what we are saying is a random function of time. That is, there can be, which means that there can be these functions, the right-hand side of that equation over there can have different representations. It can be a particular, maybe it's determined by this F of t over here with a particular F, maybe it's a different F, and so on and so forth. So the point would be that there can be, you don't really know, if you knew the function, there would be no point in my not writing down the function over there. So there is this random function which we are talking about, which means that there has to be a probability distribution for a particular F of t. And if it is a Gaussian probability distribution, it obviously has to be integral F of t square dt. So give me a particular F, the probability of, if it is Gaussian distributed, its structure would have to be that it is, the probability of finding that particular F of t is e to the power minus ft squared dt. Now the probability has to be normalized. So you would have to divide this out. All functions f are possible. I mean, you don't know the right hand side is random means that I can't give you the function f of t. If I give you a function f of t, then, I mean, it is one of many, many functions that I could have given you. And therefore, it is, if I, for a specific f of t, it is a question of, it is weighted by e to the power minus integral ft squared dt. And that is the what it would have to be. How, when would it, how would you normalize it? The normalization would be that you integrate, do a functional integral over all the df, call that some partition function z, and then the probability distribution for a given f is 1 over z e to the power minus integral ft squared dt. So this is the probability distribution for a particular f of t. The z is the normalizer. The normalizer is an integral over all functions f, and that should ring a bell. The partition function for the Gaussian model in critical phenomena was d phi, or take a Gaussian because it's quadratic, which was integral e to the power in Fourier space ddp over 2 pi d phi p phi minus p into m squared plus p squared. So that was the partition function for the Gaussian model over here. This is the z for this model over here. This quantity is f omega, f minus omega, d omega over 2 pi, and you can see the analog over here. The distribution of this is sets up a partition function, which is very like the partition function that you have been, the Gaussian partition function that you have been seeing in critical phenomena. So the maths, the phenomena widely different. The maths turns out to be quite similar. And just as we could talk about over there with the phi p1, phi p2 expectation value, over here I can talk about f omega 1, f omega 2 expectation value, and so on and so forth. So the f of t, a random function of time, means that there is a probability distribution associated with this function. I don't know the function. If you give me a particular function f of t, I can only talk about what is the probability of finding that function among an infinite set of random functions that there exist. So, all right, so that is that analogy. I mean, that's something which is interesting, and you should keep in mind. You can, I mean, thereafter calculate moments and so on and so forth. Given the moments of f, which you know, you can then, I mean, solve this differential equation over here. If I now ask you that what is Vt2, Vt1, and if I give you, if I ask you that what is the correlation function Vt2, Vt1, then I would have to give you actually the distribution
হ্যাঁ টেক্সট করেছি কিন্তু স্যার রিপ্লাই দেখে
কি বলছে স্যার, কি বলছে?
স্যার কিছু দেখেনি, মানে আমি পাঠিয়েছি স্যারকে, স্যার
তুই একটা ফোন করবি না স্যারকে?
সেটাই হবে, দাঁড়া দাঁড়া দাঁড়া,
আমি ফোন করে দেবো।
আমি করছি, দাঁড়া।
ঠিক আছে, করে বন্ধ করে দিতে পারলে ক্লাসটা।
হ্যাঁ হ্যালো স্যার, ও বন্ধ হয়ে গেছে যে, মানে মানে আমরা অনেক প্রায় 5 মিনিট হয়ে গেল, আমি কি হলো ব্যাপারটা, আমাদের ইন্টারনেট ইস্যু কি কি, মানে পুরো বন্ধ হয়ে গেছে। আচ্ছা ঠিক আছে স্যার, ঠিক আছে, হ্যাঁ। স্যার ওটা রিপিট করবে বলেছে। হ্যালো, এই হ্যালো ছেলেগুলো, স্যার বলেছে ওটা রিপিট করবে, স্যার যেমন তুই বললি পড়িয়ে যাচ্ছিল, ওকে পড়িয়ে যাচ্ছিল। হ্যাঁ, কোনটা? হ্যাঁ আইএসিএস এটা ভালো। চ এনিবে অনুপম, এটা হলো তোর মশারির ওটা লাগানো হয়েছে কি?